my entire career has mostly been around in and around marketing areas. Modeling, quantification of channels, estimation of the of the leads, and lifetime valuations, and so on and so forth. The list actually goes on and on. So today I'm going to talk about one of the projects that I did over the course of last year, and it involves deep learning, which was certainly has its own charm and affinity towards modeling nowadays, state-of-the-art technologies. But there are things that actually don't lend itself very cleanly if you blindly go ahead and start applying techniques that you've learned out there. So this, next 20 to 30 minutes, I'm going to walk you through one of the cases that I discovered that seemed to be rather odd or very peculiar. And it is not as much about the mechanics of modeling itself, but actually more about the discovery and the thought process. So there are two takeaways that you would want to take away from this meeting today. The one is, the mechanics of the modeling, which, the technique that I happen to apply in this particular situation. And not only that, but also the discovery process, why I had to pick an approach and then abandon it and then go ahead and try another approach, and what was going in my mind, what was the thought process like, and why I should be very careful when dealing with certain things. So that is, in my opinion, is actually a good insight for somebody who is out there trying to, make newer and state-of-the-art techniques and trying to apply them to their business-like situations. So let's kind of get started here, and I'll go ahead and start giving you a little introduction about the business, and so what was I trying to do, So think about marketing, and I believe that's universal, the concept that we are all sort of bombarded by all kinds of marketing campaigns in our day-to-day lives, So we think about different channels in which we get the content through. We get through advertisements, we get through emails, we get through web channels, we get phone calls or a postal email. So there are many channels nowadays that's available, and social media is being, another increasingly important channel. So, so my job here was to find out, what channel sequence is actually most potential in order to capture a lead for a particular task or a particular objective. Now, as you can see in this, a diagram out there is, I have three potential leads or candidates, A, B, and C. All three of them are getting subjected to a different channel sequence. Now, that is important because it's important to know out here, because this is actually the crux of the situation or the business context. Now, given that, almost every individual out there gets a different channel sequence, how do you go ahead and, objectively or quantify that which sequence was actually worthwhile, which ones work and which ones do not work? So this was basically my problem to solve in the context of this particular project. So if I have to give you a little bit touch point facts, so touches or the sequences can range from 1 to 100 plus. You can have any number of them depending upon the length of the campaign out there. So if you consider, 7 possibilities and just about 15 touch points. Now that is very, very moderate in these days. That means in about a period of 2 to 3 months, you're getting subjected to about 15 different touch points. And if there are about 7 channels, which are, in my opinion, is a very low number. Nowadays, you actually can get more than 10 very quickly. You land up, if you do a quick math, you land up about 5 trillion path combinations. That is a huge, huge, huge number. And not all paths are actually observable. Some, and in fact, many are not. There are very, very few possible ordered sequences or paths that you will have evidence upon. So let's say, in a large company like Vanguard, you can get away with 1 million observations, because we have been out there for quite some time. We have been out there campaigning in a very matured way. But many corporations out there, small to mid-size corporations, it's very hard to get 1 million observations in just about a year. And million is actually a drop in the ocean. If you consider that you have 5 trillion possible combinations, and you just have about 1 million or so, you have a very sparsy evidence. And that is where I want to put this whole project or this whole context into your mind before we actually proceed further, because this is going to come back and start biting us later. So this is the context that we have. We have 5 trillion possible combinations, and if you have observations of just about 1 million. My objective here is, again, to find out which combinations are potentially viable and which ones are actually not so viable. So let's get started. If you are in the deep learning space, you have to have known that RNNs actually do a good sequence modeling. So I was not an exception here at all. So what I did was just picked up this architecture and then applied it to the sequences. And here's what I start to find. I put in, I've just numbered these the channels. Instead of naming them as phones and advertisements and web, etc., I've just numbered them as 1, 2, 3, 4, 5, 6. Each number, just for simplicity, and each number represents one channel. So if 1 is advertisements, 2 could be phones, 6 could be web. So consider that as just a numbered form of the channel. So when I do this, I find that if I apply a channel sequence as 1, 1, 2, 1, 6, and then I simply flip one position. So let's begin. So 1, 1, 2, 1, 6, I get a score of 0.5, which means there's about 50% chance that this particular sequence is going to get converted into a customer. If I flip, one position, that is, instead of calling it as 1, 1, 2, 1, 6, I do 1, 1, 2, 5, 6, which basically means that I have flipped one channel. Instead of a phone, I may have just gone in for a web. I see that the odds to conversion actually jump from almost 50% to very close to about 1. 1, it typically really means that you are nailing it. You're actually getting the lead inside your customer zone. And then again, if I happen to just flip the same channel onto 0, which 0 actually means nothing, means basically do nothing, the odds of conversion typically fall right from 1 to about 0, which means you've basically lost a candidate. You've basically lost that particular lead. Okay. Now, if you as a modeler or as a scientist trying to discover that what channel sequence I should go by, if you had modeled this through this particular architecture, you would find that, okay, I should pick 1, 1, 2, 5, 6. Okay. But then there is something in you that actually tells, just by flipping one particular channel, I'm shifting my odds ratio from 47%, to be more precise, to about 99%, and then again to about 0%, which basically means I'm increasing my odds of conversion to 2 folds, and then again dropping to 0. Now that sounds, fishy. That sounds odd. That sounds like, how can just one channel in one particular spot can make so much of a difference? So that caused me thinking, and this, my first thought was maybe I was not modeling right. Maybe I was trying to do something, or maybe I'm overfitting the data. Or I wasn't tuning it appropriately. But trust me, I went around for a number of days from here point to trying out many different tuning parameters, many different times cross validation, and the both test scores and the test accuracies and the train accuracies were pretty good. They were all above 90%, closing to about 95% each and every time. And yet I continuously saw this behavior over and over again. So that got me thinking. What was going on in there? What is it about these points of discontinuities? When I say points of discontinuities, basically means that extremities, 99% and very close to 0%. What is it about them that why is the architecture literally swinging in both the directions very, very widely? Okay, so when you go around and so I started to discover, I peel the onions, go down to the depths of it, trying to see what was actually going on. There were there's one thing that actually caught my attention. If you look at the bar below, red means basically red means the positive cases, and no means the negative cases. With respect to that particular channel sequences, were actually unbalanced, completely unbalanced. So if you see out here, if you look at the second bar, which has a long range of red, which typically means there were a lot more positive cases on that particular sequence, and if you look at the other bar, you actually see there were a lot more negative cases on that particular sequence structure, and that was actually crux of the problem. Now, why does this happen? If you go back and I refer to my first slide, which typically says, if you look at it, I had 5 trillion combinations, and how much evidence I had? Just about 1 million. That means my entire universe was basically sparsed, spotty. There was vacuum. There was actually nothing out there. There were no observations, either positive or negative, good enough in number for this architecture to actually capture. If the space was filled, then great. I would have all possible balances and counterbalances in either directions. The world will be perfect. Things will just go on from there. But so in this context, and this is why I wanted to actually point out that if you go ahead and blindly go ahead and apply an architecture, and if you walk away with a result like this, you're going to be grossly inaccurate. And that is where I wanted to call out that when you apply things and the results don't fall into favor or something that catches your attention, do not trust it. Stop, reflect, go back and see what was actually going on in there. So coming back to this problem context, so it was very prominent and the data size was small compared to possibilities. This is where these things start to appear. They will not show up, when the ratio of evidence to the possibility is good enough. This will not show up, but this will show up very, very, very quickly if things go out of hands. More skewed the strength of evidence and higher the discontinuities, you're going to start facing them. Okay. You try out different kind of parameters. It's not going to help out much out here. There is something else that is actually going on. So what did I do? And why? So basically, when you catch these things, when you catch this attention that things are going wrong, you go ahead and start. As a scientist, you start to go and try to uncover the root cause of the problem. Data is okay. It's just that it's incomplete. That is one thing that we have already discovered. And in this situation like this, you're hardly ever going to get a full, clean subset. I mean, if you're typically working in corporations, you're away from the academia and you're working on a real-time information, it's going to be noisy. It's going to be, half, out there. half incomplete. It may even be that, in this particular situation, you may not even have all the number of, good number of observations even to go ahead and deal with it. So this is what basically goes and starts hitting you if you're not, it's not the fault of the architecture itself. It's actually, the situation, the context, and the data that is actually causing it. Now, what I discovered that we have been modeling symptoms, not the true features. Okay, and I'll get back to you on this. So there is something that is underlying that is reflected into a channel sequence, which is not the feature. It's just a symptom of an underlying feature. Okay, longer the sequence and the worse it's going to get. Just so because the more higher the sequence, the possible universe is going to grow exponentially. Okay, higher the numbers of channels, again, is going to get worse because the possible space is going to exponentially expand, and you will only have that much of data to actually go ahead and deal with it. Okay. The one other thing is that you can collect more data, but the problem is that good and clean data is hard to come by. Okay. It's going to take you years before you can get to even closer to that. But what's going to happen, if more you wait, the business conditions change, the policy changes, the strategy changes, and it is no longer the same data that you actually went out in the first place with. Okay, you're going to get a different forms of data now, so it's not going to solve that particular problem. And then one thing always comes back to a scientist at all the time: what is my confidence in these results? Is there is it large amount of uncertainty in which I can report on? So these are the other things that you have to grapple with when you're trying to solve, a situation like this. So remember, is modeling mechanics is one part of the story. This, making sure that what you have discovered is appropriate. What the kind of assumption that you put in is appropriate. What your thought process, because you are the only one who knows the best about the problem at that point in time. Okay, no one really, and you are the best judge. You're making your decisions every single point going onwards. So you need to be very careful, whether you are in the right direction or not. Okay. So now getting into a little bit of mechanics of the model, I may not have enough time to actually explain the whole thing, but I want to leave you with these slides, and I have the references for you to go ahead and start reading it. But one thing I wanted to give you on next couple of slides is just a little bit of the mechanics out here about. So what I did was something I wanted to get away from the symptoms and get on to the true features. Okay. Now, to obtain any kind of true feature, you need some sort of a regularization in place to play out with. Okay. And variational encoders or variational autoencoders are actually one of the many architectures that are has been very potentially to deal with. They have mostly been applied towards some sort of generative algorithms, and and this is all actually not different either. We are also going to create or do some sort of a regularization through generation of the mechanisms here. The architecture is fairly straightforward, and it's now is widely published in the course of last 1 year across many places. So all I'm doing here is, instead of modeling through an RNN architecture directly, I'm actually extracting features from the RNN and basically reflecting or imposing them onto my latent dimensional space. That's a central piece that you're out here. Now, there is one caveat out here, is that how many dimensions I must choose from. It's actually, it's a good area of research, but I can actually point you to, if somebody's interested, you can reach out to me and I can point you to the right direction in the number of dimensions. For now, let's stick with, you have 2 dimensions just for the simplicity of it. Okay. When I project these points onto this dimensional space, now due to its variational in nature, remember, it's not an autoencoder. It is a variational autoencoder, which typically means that instead of a point projection, I'm going to project a distribution, okay, the entire space is going to be filled up with informational space in this, and we'll see the latency, but how does it look like in a moment here. But so think just in terms of analogy, think, if somebody's a physicist out here, you would map this to a point or a particle versus a waveform. So distributions are like waveforms, and a point is basically a point or a particle, if you give an analogy of space. And then once you have once you have projected that distribution onto the latent space, you can actually then go ahead and start generate sequences from it, and run through a typical classifier, and sort them out in a way that they get, the good ones get clustered together, and the not so good ones will get clustered together. And we'll shortly see how the space actually looks like. Just for the completeness, the architecture, formally is called a disentangled variational encoder, because you do a disentanglement just good enough to make sure that the clusters are well formed. That's why this disentanglement comes in from. There is a loss function. I just put it up here, and we can. I don't want to get into too much of mechanics here. We're going to lose your thoughts, but continuing with the flow, I wanted to give you the. Okay, I think this is the follow-up slide about the loss functional here. I've given you a little bit of a direction in terms of what is getting projected. So remember that in the central piece that you see with the dotted lines is actually the loss function. The beta out there is the disentanglement parameter. Okay, this parameter is something that is for you to tune on. Okay, and it really depends upon data set to data set, and this is something that you can't put a number on it heuristically. Okay, the other pieces are just the regularizer. Choice of prior out here is Gaussian, but you can basically pick any other prior in terms of regularization effects. Okay, and the last term that you actually see, which is log p of k by z, is nothing but a classifier on it. Okay. Again, I don't want to get even too much into the mechanics of this equation, given the paucity of time here. But I certainly wanted to show you that you extract features from an RNN architecture, project them to a latent space, and pick out your pick out the points, form a cluster. Formation of a cluster will happen through this given architecture, and pick out the points from the cluster that you want to pick it out from, and basically that will give you in some sort of an ordered sequence in which will be regularized. Will have the contained information of true signal minus the noise as much as possible. This is what I wanted to show you in terms of latent spaces. Everything out here is nothing but, this is the central idea. This is the latent space that you actually see. So on the left side, when you begin your training process on the epoch 0, this is what the space will look like. I've just projected them to a two-dimensional. The red ones are the negative cases, and the green ones are actually the positive cases. Okay. When you move from epoch 0 to epoch 10, which is fairly moderate, and you can go up to 100, you would see that the space is getting formation is creating a cluster. All the green ones are now getting tied onto a one spot, and all the red ones are actually getting clustered together. And as you go on with it, you will see that these clusters are very well formed. Just at the time, and this is something that you'll have to decide on your data set. This is what I call that as disentanglement. And whenever the disentanglement is good and well formed, I think you can actually stop the training. In this particular case, 2 dimension and disentanglement factor was 4. That was my case on this particular project. And once you have this, if you look at the bottom right corner, you see that you can actually do to a latent space algebra or arithmetic out there, which typically means that if you're on a point A, and if you subject to a particular channel, how this point A is going towards, whether it's moving towards a certain desired direction or is moving away from a desired direction. Let's see that in a moment here. Okay. I think these clusters are now sort of well formed. You also want to test, again, a test phase, basically a holdout data set, making sure that your training is appropriate. So this is where I show that the left side is a training data set, and on the right side is actually a test data set. You'll possibly see that they are both very well formed, except that the one on test will have some extra noise because it's basically a test set. So once you have formed this formation of good clusters, your training is sort of complete, and then you can go ahead and start applying any kind of a latent space algebra on top of it to figure it out, where I am and where I should be going towards. Okay. I also wanted to show you how the spatial density actually looks like. Remember, the points that you actually saw over here, they're actually not the points. They are the waveform. They are, what I plotted is only the central mean of it, but actually it is a waveform, which typically looks like one in the diagram on the right. This is the actual picture that you're going to actually basically see. Is filled with distribution, is full with waveforms. You see the light zones, that's where the signals are sitting. You see the darker zone, there is an absence of signal, which basically is filled with noise or random, just randomness. And you form, basically these clusters, these solid densities will form in your data set, okay? Once you have these densities formed, you can basically go ahead and start doing algebra. But let's go back to our same example and see how this actually behaved versus what we were doing with original RNN architecture. This one I've called it as RNN plus Bayesian. It has variational elements to it. And now you actually see that the blue line is our original line, which actually moved. I've just normalized it in terms of the y-axis here. So but the shape is exactly the same. You see that the blue line is moving up in the same direction, but the greenish line, which is the Bayesian part of it, does move up, but it does not move up, tremendously. And same is the behavior you're going to see on the flip side as well. You see the RNN dropping down from the heights to the lows very rapidly, versus the Bayesian structure does not do that, because it has now been regularized, and it is now trying to capture the true features instead of symptoms. So I call that as, in the former architecture, we were modeling the symptoms. In the latter architecture, we are modeling the actual true features of it. You see that there is a good level of consistency amongst the different codes, and this seems much more reasonable. I do expect some variations to happen, but at the same time, I don't expect that just by flipping one channel in some particular sequence, the odds should dramatically swing in one direction or the other. Okay? I wanted to show you the other part of it, which is you can actually derive something called next best action from this. Now imagine this is your latent space. Okay, you are at point A, which is somewhere on the north of the red cluster. Basically, your odds are not that great because you're sitting somewhere in the red zone, okay? And you want to get what you want to do is basically try to get onto a point in the green cluster, okay? And and what's going to happen is if you and you know basically what step I should do next onto a channel sequence which is A, so as I can go towards a greener zone. So if you see in this particular diagram, I'm trying to show here, and I don't know how clearly it's visible, but it's like if I subject them to a channel 5 or a channel 7, I happen to move the point A more towards a greener zone. Okay, so I have a pick on the channel. So it is not that I have to randomly now pick any channel that I can go by. I have a closer subset. I have a better shortlist. Instead of working through 10 random channels, I know I can only work with 2 because that is going to give my point a lift into a greener cluster. Okay, so this is what I call as a next best action. So given where you are and where you want to be in your next step. Okay. So so with this, there are a few takeaways. I wanted to actually call them out. So smaller data sets, RNNs actually, a regular typical RNNs will memorize the sequences, and that's been very nasty. We have known that forever, and it gets worse when your possible universe is much larger. So it's not going to very clearly show up, if your possible space is small, you have good enough data observations. So I think they do just fine, but it's only when the things are in a very alternate ratios, then you'll see these things happening. One of the things is that you can weigh the sequence's strength by the evidence is seen. That is, that's one other approach, which I have not taken up here for, instead I've taken up a latent space approach. So what I'm saying here is basically do not model the symptoms. You can always extract best signal to noise ratio in a latent space and regularize them through your distribution. That's the Bayesian part of it. And in this particular, if you're taking this second approach through a Bayesian modeling, I think one of the things you do need to consider is about a disentanglement factor. That comes purely a big pure play based upon your data set. If you have to ask me now what approach I should go ahead and take it, I would say 2, 4, 6, given the even numbers of beta, and really you possibly would need to go beyond 6 in my opinion. Try with smaller and then go ahead and increase your disentanglement factor just enough to a point where you see a good formation of clusters. Okay. The next best action is actually a bonus on this particular approach. It may or may not be available for anything and everything that you want to do, but at least on this particular fact, it comes out very naturally to me. The downside is that you have to train actually 3 different architectures, 3 different models, all built into one. And that takes a much larger time to tune and much larger time to actually train. So it's computationally expensive, but once you have got a good latent space, I think you're good to go from that point onwards. These are the references I've used in doing that. I certainly encourage you to read all the references, including the last one, which is the elbow surgery, which gave me a great insight about what was happening in terms of variational autoencoders. Okay. Lastly, I want to leave you with certain thoughts here. Think like a scientist. That's the main purpose of it. Modeling, mechanics of modeling it will come by enough practice. But if you're not curious enough, if you're not, very sensitive to your outcomes, you're going to miss these things. You're going to glossily overlook them. And what will result is that you're going to start reporting things which is inaccurate, which may not be satisfying. And remember, if you're situated in the thick of a business decision process, there is a lot that is banking on you, you alone as a person. So you got to be very sensitive and responsible around, what you actually go ahead and report. Many times, the other thing is about the assumptions that you make as a person, assumptions that data that is coming in has got a built-in assumptions on it, and the model itself makes a certain level of assumptions. So be very cognizant of the assumptions that are being made in this, any kind of modeling architecture that you actually go ahead and pick, because if the assumptions are not valid, your outcomes are going to be invalid very quickly. And lastly, the intuition. The intuition really comes from the business context or the space, if a person is into. So in this particular situation, I've been into marketing for almost a dozen years now. And if you are new to that space, so these things will not cross your mind that a simple flip of a channel is actually, causing more harm than good in the modeling process. So things should actually start to cross your minds. If they don't feel right, they probably are not right. And lastly, you as a scientist, hardly ever you will see that, data is clean, one-step process, you model, and the other goes the outcome, and everything's over. No, rarely that will happen. Data is not going to yield itself to the expectation that you want it to come on the other side of it. So what do? You innovate. You change your direction, you change your approaches, you try out multiple approaches, and until you're fully satisfied with yourself, you're actually not going to proceed any further. So these are the thoughts I wanted to actually leave you with. I hope you enjoyed my conversation. I hope I'm on time here. I had only 30 minutes to do that. And over to the moderators, if you are in there.
Thank you, Vishal. That was very informative and jam-packed information. So we have one question. I believe we have two questions now. So Isaki asked, is there any other sources to get to know about the process and your results in detail?
Yes. So let me put it up this way. If you can send me an email, what I've done is I've posted a lot more detail and actually the code itself to a GitHub. So I will, if you can shoot me an email, I can respond to you with much more information. Some of the materials and actually the code set and the what do you call them as and the data on which this was performed. So you will have that information with you if you send me or contact me afterwards. There's a lot to go through. I've skimmed through a lot of details here, but I know it's a lot to grasp actually on this. It's not a 30-minute thing. It's actually many hundreds of hours. I'll go into it.
So Isaki also asked about your email address.
Yes. Neeru, I have given it to the panel, and if you can go ahead and share it, that'll be great. Or I can, if I can, I don't know if you have to type it. I can type it.
Okay, I'll see to it.
Yeah. Okay, thanks.
Krishnan Raman raised his hand, so I asked him to join. He can ask his question through voice chat. And another question is from Stephen. He's asking, could you please briefly skim back over the path modeling slides?
Okay, sure. I can go back to the path modeling. Is this what you're looking for? Like, is this a slide that you're looking for, or is this the slide that you're looking for?
You can raise your hand if that's right, Isaki or Stephen. Okay, moving on. We have another question from Jamie. The question is comparison to other methods, comparative performance, particularly the cost of finding an optima.
I think I lost you.
So Stephen said that is the slide he was looking for.
Okay,
So
excellent.
the question, Jamie's question is comparison to other methods, comparative performance, particularly the cost of finding an optima.
Oh, is that the question? Enough? Okay. So,
I think the question is not clear. So anyway, the time is up for this session. Thank you all for Q&A, and thank you, Vishal, for this informative insight. And we'll post all the recording after the conference. And
yeah, sure.
we ask all the attendees to put on the social media with the hashtag global AI, and tweet and put all the interact with each other. That way you can network also. So we have to start the next session.
Okay, thanks, Neeru. And I'm happy to chat with you on an email if you feel prefer so. Thanks, guys.
Okay, thank you, Vishal.
Hello.